In this video, we shall take a closer look at work and kinetic energy. We shall also look at a principle that connects these two important quantities. Let's look at kinetic energy first. We know that kinetic energy is a form of energy and therefore it is measured in the units of joules. It is also a type of energy that is associated with motion of an object, which means it is dependent on the speed of that object. Indeed, if you have an object that is moving with a speed, say v meter per second, and the object's mass is m, then the kinetic energy is defined as half times the mass of the object times the square of the speed of the object. In order for the kinetic energy to be quantified in the units of joules, the mass must be expressed in the units of kg, and speed must be expressed in the units of meter per second. From this expression, it is clear that when the object's speed is 0, the kinetic energy is identically 0 as well. So it is as simple as that. Now let's look at the concept of work. As before, let's assume you have an object whose mass is m. The object is being acted upon by a bunch of forces. Say in this case, a couple of forces. The net effect from such an action is the object is getting displaced from its original position, say by an amount x. Of course, now we assume F1 and F2 are constant. So since the object is moving to the right, say with some acceleration a, then we know F1 is greater than F2, and there is a net force involved. The net force in this case is F1 minus F2. The direction of this net force is to the right. This net force is the force that is displacing the object at distance x to the right. So in this case, we say there is work, a net work that is being done on this mass m, and that net work equals the net force that the object is subjected to times that displacement x. More accurately, work is defined as dot product of force and the displacement vector. So in this case, because the net force is in the direction of I hat and the displacement vector is also in the direction of I hat, when you take the dot product of these two vectors, you end up with that expression. So at least for one-dimensional case, the concept of work is relatively more straightforward. Let's look at the same system from another point of view. Let's calculate the work done by F2 and F1 separately and then determine the net work from those two numbers. So let's determine the work by F1. It is given by, as we said, dot product of that force F1 and the displacement x. So since the direction of F1 is to the right and the displacement is also to the right, this will give you F1 times x. Now what about the work done by the force F2? F2 is going to the left, so that means is minus F2 I hat dotted into x I hat. So that's going to give you a negative work. Work can be negative. It is negative when the force that is producing the work is opposite to the direction of displacement, like in this case. So from these two numbers, we can calculate the net work. The net work is just the sum of the two works, W1 plus W2. So since W1 is F1x, W2 is minus F2x, when you combine the two terms, you get that. The same expression we found a few minutes ago. We stress here that in this video, we are dealing with just constant forces, meaning their magnitude and direction are the same all the time. Now let's bring these two concepts together, the work and kinetic energy. So let's assume we have an object. Initially, it is moving with the speed v1, and at some later time, it gets to another location, another position, and at that moment, the speed is v2. Now let's assume that v2 is greater than v1, so the object is accelerating to the right, like that. If it is accelerating to the right, there must be a net force acting on this object as well. That's from Newton's second law. So net force on this object equals its mass, say m, times that acceleration. Let's also assume the object is displaced by a distance d along the, say, x-axis. We mentioned that the net force is constant. At least that is the case that we are considering in this video. So that means the acceleration is constant. So we are dealing with kinematics. One of the kinematics equations that relates v2, v1, the acceleration, and displacement is as follows. v2 squared minus v1 squared equals 2 times the acceleration times the displacement. Remember this equation? It can be found in our previous video on kinematics. Now let's multiply this equation with the mass of the object. And if we do that, we get the following result. mv2 squared minus mv1 squared equals 2 times ma times d. Remember, ma is the net force. So we can substitute ma with the expression F net, and F net times d is the work done by this net force on this mass as it is displaced a distance d. So we can simply write it as 2 times the net work. Moving the 2 to the left-hand side, we see that the net work done on this object equals half m v2 squared minus v1 squared. Now this term is the kinetic energy at location 2, and that term is the kinetic energy at location 1. So K2 minus K1 is essentially the change in kinetic energy of the object as it moves from position 1 to position 2. So that is the expression that we were looking for, which says the net work done equals the change in the kinetic energy of the object. And this expression is known as work-kinetic energy theorem. Now let's look at some problems associated with these concepts. Problem 1. A sled filled with wood is pulled by a tractor as shown. So you have a tractor pulling a sled, and inside you have wood. The total work done by all forces is 12,000 joules. So we are dealing with the net work here, and net work is 12,000 joules. The mass of the sled is 1,800 kilograms. The initial speed is 2 meters per second. What is the final speed? So when we apply the work-kinetic energy theorem, it simply states the net work done equals the change in kinetic energy. The net work is 12,000 joules, and the change in kinetic energy is half times the mass of the sled, 1,800. The final speed is what we want to determine, Vf, minus the initial speed, which is 2 meters per second, so 2 squared. And we can determine the final speed that way, and it turns out to be 4.16 meters per second. And that is the solution to this problem. Problem 2. In a pile driver, a hammerhead, so that is the one in red, with a mass of 250 kg. So the mass of the hammerhead is 250 kg. It is lifted 4 meters above the top of the vertical beam. So that is the top of the vertical beam. Then the hammer is dropped, causing the beam to go 8 cm further in the ground. The rails that guide the hammerhead exert a friction of 100 newtons on the hammerhead. So as the hammerhead falls down, these rails on the side, it exerts a frictional force opposite to the direction of that falling hammerhead. Now, what is the speed of the hammerhead just as it hits the beam? Of course, we assume that the hammer takes off from rest, and we want to determine the speed when it hits the beam. Let's look at all the forces that is acting on this hammerhead. First is, of course, its weight, which is 250 times gravitational acceleration. And then you have this total friction of 100 newtons heading upward. So that means the net force acting on the hammerhead is 250 times g, the weight of that hammer, minus the friction, which is 100 newtons. Using 9.81 for g, we get 2,352.5 newtons for the net force. Since it's falling a distance of 4 meters, the net work on that hammerhead is the constant net force that we have calculated times the displacement, in this case 4 meters. So 2,352.5 times 4, and that's going to be 9,410 joules. Now, using the work-kinetic energy theorem, we see that the net work is 9,410 joules. The change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Initially, the object, or the hammer in this case, is not moving, so the kinetic energy has got to be 0. At the final location, it has kinetic energy because it has certain speed there, which is what we want to determine. So kinetic energy at that point is half times the mass of it, which is 250 kg, times Vf squared. And we can determine the final speed. It is 2 times 9,410 divided by 250 square root meter per second, which is about 8.7 meter per second. And that's the answer. Thank you for watching.